All right, so this is chapter 7. We did test 3 in general is the normal distribution and sampling distributions. So chapter 7 is talking about sampling distributions. So the whole purpose of sampling in general is, remember, a lot of times we can't ask every single person or thing in the population. So we just look at a sample of X bar and P hat. That is their actual names. So this is called X bar. This is called P hat, like P with a hat. That's literally what it's called. So the central limit theorem for sample means we have a population distribution, which is the population distribution of the population data mu. That's what we did in chapter 6. And then in chapter 7, what we're going to do is the same concept, but for sampling, a sampling distribution, which is the probability distribution of a sample statistic. That sample statistic is our X bar. The probability distribution of every possible mean or proportion. Proportion, remember, means our percentages, given a specific sample size. So proportion, remember, means just our percentages. So a sampling error is the difference between the value of the sample statistic and the population parameter. So for example, the difference means subtracting. So we are subtracting the sample statistic, which is X bar, and then for our population parameter, which is our mu. So our sample mean minus our population mean. So sample mean minus population mean. If we're trying to find the error, our population mean is the actual like thing that we're trying to find, and our sample mean is just the sample of it. So the difference in those two is our error. So that's a sampling error. But a non-sampling error is another error that can occur, but it occurs in the collection, recording, or tabulation of data. It's like a human mistake. So it's just a typo. So whenever you're recording something, if you write down the wrong number, for example, it's going to give you an error in your answer, but the error is caused by a typo more so than the actual statistics part of it. So that would be a non-sampling error. So the symbol for the mean of a sampling distribution of X bar, I know it's like a mouthful. So the mean of sampling distribution of X bar is going to be, our mean is mu. But for a sampling distribution of X bar means that we're going to show that by doing a little subscript. It's a little subscript of X bar. And we say this, let me use a different color, as mu sub X bar. Mu is that population mean. It's a subscript, so sub X bar is our sampling mean. So this is the mean of sampling distribution of X bar. Same thing for the standard deviation. The symbol for the standard deviation of the sampling distribution of X bar is the standard error of the mean or the standard error in general. So standard error of the mean, standard error is going to be, standard deviation is sigma. The standard deviation is sigma. We're talking about the sampling distribution. So to differentiate it from our regular sigma, we're going to do sub X bar again. So this time it's going to be sigma sub X bar. Sigma sub X bar. The standard deviation of the sampling distribution of X bar.
Bless you.
Thank you. Also known as the standard error of the mean or just the standard error in general. Ryan, go for it.
So mu, like when one thing is wrong, as standard is when everything is wrong.
So mu is for our population, mean. So this is talking about the mean, and sigma is for our standard deviation. Which is normal, but the little X bar just tells us that it's a sampling distribution. Sampling distribution is what we're going to talk about in this chapter. Thank you for bringing that up. Anything else? So we have formulas for this that we're going to use, and these formulas are on our formula sheet, which is on the last page. Remember, you get to use this formula sheet on the test as well as your tables if you want to use the tables. So here are our two formulas that we're going to use. The formula for our sampling mean is just going to be our population mean. So they equal the same thing, just our population mean. And our standard deviation of our, notice it's sigma sub x bar. So standard deviation of our sampling distribution, which is a mouthful, is going to be our population standard deviation over the square root of n. So this is the only thing that's different, is this time we have a little bit different standard deviation. We have our regular population standard deviation. Bless you. I think it's this pollen. I hope it's pollen. No, I'm just kidding. I know mine's pollen. Maybe it's the room. Seriously, before they clean the carpet every semester. But I feel like at the end of the semester, the carpet gets so dirty. Yeah. I feel like everyone, I don't know, maybe I'm allergic. Maybe I'm allergic.
They don't vacuum it regularly?
Oh, yeah, vacuum it regularly. But like, I mean, yeah, they take everything out and like shampoo it or whatever. And it smells so much better. I'm like, oh, can you do this?
They don't even vacuum out.
No, they vacuum it. What? Yeah, maybe. But think like everyone bring like their shoes and stuff. Like there's a lot of traffic in this room. So, or in every room. They do every room. But so all over the square root of n, which is our sample size. So think about it. Whenever we're doing our mean, that's just our mean, but whenever we're doing our standard deviation, we had our population, and then we're taking a subset of, we're taking a sample, so we have to account for that sample. So that's where we account for it in the standard deviation. So the central limit theorem says that with a sample of n being greater than or equal to 30, they just say that you have to have a big enough sample, and they just pick the number 30. Don't ask me why. But that's what the central limit theorem says. It says a sample size that's large, so n is greater than or equal to 30. The sampling distribution of the sample means within a population mean and standard deviation will be approximately normal. Just like from chapter 6, it'll have that nice bell-shaped curve, and we can use all of our stuff that we talked about in chapter 6. And then we can use these formulas. So it says our mean for our sampling distribution is going to be the same as our population mean. So our sampling distribution mean equals our population mean. And our other formula, our sampling standard deviation is going to be our population standard deviation over the square root of n. Basically, it's saying if the central limit theorem says that if we have a big enough sample, we could actually do something with it. We could actually do something with it, just like we did in chapter 6. We're going to see that in a second. Note that the central limit theorem allows us to standardize data to z-scores and to use to use the normal distribution tables to find probability regardless of its shape or characteristics of the underlying distribution. So if it has a large enough sample size, if our sample size is greater than or equal to 30, we can do just like we did in chapter 6. We can change it into z-scores. We can put it to our calculator, find the area to find the probability, all that good stuff. So our first example says, consider the following scenarios and determine if the central limit theorem may be applied or not. So it says a population distribution has an unknown distribution shape, and what that means, unknown distribution shape, just means I don't know if it's normal, I don't know if it's skewed, I don't know. So could I say IDK for I don't know? So I don't know if normal or not. So we don't know if it's normal. The mean is 436 and the standard deviation is 36. Our sample size of 61, that's the big thing here. Our sample size of 61 is drawn. Can the central limit theorem be applied? Yes, because our n value is 61, our sample size, which is greater than or equal to 30. So we're good to go. So B, yes, the central limit theorem can be applied. Next example, a population distribution is known to be skewed to the right, so I automatically know it's not normal. So just by knowing that, I can't do chapter 6 stuff unless I can apply the central limit theorem. So it's skewed to the right with a mean of 251 and a standard deviation of 35. Our sample size of 34 is drawn. Can the central limit theorem be applied to this sample of the population? So again, because our n value, our sample size is 34, it's greater than or equal to 30, so we're good to go. Yes, the central limit theorem can be applied.
That's all you have for that.
That's it. There's 2 more examples on the next page that'll kind of explain more. I try to put every scenario. So the first one, we didn't know the shape, but it didn't matter the shape because our sample size was big enough. The next one, we knew it wasn't normal, but that didn't matter because our sample size was still big enough. So I can generalize it using the central limit theorem. Ready for the next page? Other 2 scenarios. So the first one says a population distribution is known to be normally distributed. So it's already known to be normal, with a mean of 249 and a standard deviation of 53. Our sample size of 29 is drawn, so it's not big enough. Can the central limit theorem be applied? So because our sample size is not big enough, it's already normal though. So I don't even need to apply the central limit theorem because it's already normal. It's already able to be done like chapter 6. So it's already normal. So we're good to go. So yes, the central limit theorem can still be applied because it's already normal. It already has that nice bell-shaped symmetric curve. Last but not least, population distribution is known to be skewed to the left, so it's not normal. So if we know that it's not normal, it has to have a big enough sample size. Our mean is 443, our standard deviation is 67, our sample size of 11 is drawn. Can the central limit theorem be applied? No. So our n value, our sample size is 11, which is not greater than or equal to 30. It's not big enough. So no, the central limit theorem cannot be applied. That's it. That's all we have to do for those. Questions on those before we go to an actual, like, getting into it slowly but surely. Next example, a population distribution has a normal distribution with a mean of 487 and a standard deviation of 83. You intend to draw a random sample of size 81. Determine the mean and standard deviation of the sampling distribution of X bar round to 4 places if needed. All right, so I'm just gonna, just like we did before, write down everything they give me because I don't want to look in this whole paragraph. I kind of just want to like say, okay, here's what they give me, and then go. So they tell us our mean, our population mean is 487. Our population standard deviation, our sigma, is 83. And our sample size n is 81. So just by looking at our sample size n of 81, That's greater than or equal to 30, so we're good. So the central limit theorem can be applied. So the central limit theorem can be applied. So I can use these formulas to find this answer. I always get the question, they're like, well, what happens if we can't use central limit theorem? There's not going to be a problem that's like setting you up for failure. That's asking for these answers, but you can't use central limit theorem. So don't really worry about it. I just wanted to kind of point out that we're able to do this here. We're able to use our formulas. We're able to use the central limit theorem because our n value is greater than or equal to 30. The central limit theorem says that the mean of the sampling distribution of x bar, mu sub x bar, is the same as just our population mean, same as mu, which they told us in the problem, 487. Done. Mu sub x bar is just the same thing as mu, so it's 487. The central limit theorem said that the standard deviation of our sampling distribution of x bar, sigma sub x bar, is going to be sigma over the square root of n. Sigma, they told us, was 83 over the square root of n, which they told us was 80. So in my calculator, 83 divided by the square root of 81. Let me show you how you can put it in your calculator just in case you need it. So 83 divided by the square root, which is right here above x squared. So second x squared, 81. And we get 9.22222. It said to round to 4 decimal places as needed. So 9.2222. Done. That's it. Let's look at the next one. So it says, suppose the standard deviation of the ages of all Florida Panthers is 14.1 years. Let X bar be the mean age for a sample of a certain number of Florida Panthers. What sample size will give the standard deviation of X bar equal to 4.1 years? Notice it says round the solutions up to the nearest whole number if needed. All right, so just like the previous problem, let's see what they give us. They tell us the standard deviation of all Florida Panthers. So that word all, that means our population standard deviation. So that means our sigma is going to be 14.1, population standard deviation. Let X bar be the mean age for a sample, blah, blah, blah. What sample size? So we don't know the sample size, so it's asking us to find n. So what's n? We don't know n, we're going to look for n. We'll give the standard deviation of X bar. So standard deviation of X bar, so sigma sub X bar, equal to 1.4 years. So it tells us our population standard deviation is 14.1. And it tells us that our standard deviation of X bar is 1.4. So I could use our formula. Our formula says sigma sub X bar equals sigma over the square root of n. That's the formula we've been using. This formula is on your formula sheet. So speaking of our formula sheet, it automatically solves it for you. So if you were to take this and solve for n algebraically, this is what you would get. N equals sigma over sigma sub X bar squared. So it already gives us that formula on our formula sheet. So let's use it. So if I were to solve this for n, I'd multiply both sides by the square root of n. Divide by sigma sub X bar, square both sides, but we don't have to worry about that because it gives us the formula. So n equals sigma over sigma sub x bar squared. And I write a little note, this is on your formula sheet. So we know sigma is 14.1 over sigma sub x bar, which we know is 1.4 squared. So just like I see it in parentheses, 14.1 divided by 1.4 squared. And we get 101.43 blah, blah, blah. 101.43 blah, blah, blah. Notice it says round the solution up to the nearest whole number. So forget about rounding rules, always round it up. So we're talking about Florida Panthers, right? So it's saying 101.4 Panthers. I don't want 0.4 of a Panther. So always round up to the nearest, to the next whole Panther. Yeah, whole number. So 102. So whenever you're finding n, always round up. And I put this here, always go up to the next whole number if the sample size is a decimal, regardless of normal rounding rules. So you don't want point of a part of a Panther. So always round up to the next whole number. Whenever you're finding n, only for n, always for n. Questions on that one? All right, so kind of going back now to chapter 6. So it says calculating a z-score for a sampling distribution. So we have z equals x bar minus our sampling mean all over sigma sub x bar. Remember that our population mean is the same as our sampling distribution mean. So I can write that as x bar minus mu over our sampling standard deviation. And then we also know our sampling standard deviation is sigma over the square root of n. So if you kind of want to put it as one big formula, we have x bar minus our mean all over sigma over the square root of n. I know it's a complex fraction, so we usually don't write it like this, but this is kind of like everything you need to know in one shot. And this is on your formula sheet. Flip in there real quick. Z equals x bar minus our mean all over our sampling standard deviation. And we know our sampling standard deviation from right up here is sigma over the square root of n. Sigma over the square root of n. All right, so this looks super similar, by the way, to our formula from chapter 6 for our z-score, which was x. So now we have x bar, we're talking about sampling, minus our mean, still minus our mean, all over our standard deviation. Now our standard deviation is for our sample, so that's why it looks a little bit different, sigma over the square root of n. But it's still the same concept. So our example says, consider the population of size capital N equaling 11,200 with a mean mu of 152 and a standard deviation sigma equaling 28. Compute the following z values for the sampling distribution of x bar with a given sample size, round to 2 decimal places if needed. Now cut the problem off, it goes to the next page. Before I do that, I want to write a little note. So go to next page. It's like part of the problem. But I wanted to write a little note. So n is going to be our population size. So our capital N is population size, lowercase n is our sample size. Lowercase n is our sample size. It gives us our population mean of 152 and our population standard deviation of 28. Let's take this and go to the next page. Suppose a random sample of 56 observations, so this is our sample size, this is lowercase n, is selected from the population. Calculate the z-value that corresponds to x bar equal 145. All right, so it tells us, let's write our givens. So n is 56, x bar is 145. On the previous page, it told us our mu, which is the same thing as our mu sub x bar, which is 152. And our population standard deviation, our sigma, is 28. It asks us to calculate our z-values. So we know our z-value is going to be x bar minus our mean all over our sampling standard deviation. We know our sampling standard deviation is sigma over the square root of n. So just our formula that's on our formula sheet we talked about on the previous page. We're just going to plug in everything from the formula. So x bar is 145 minus our mean, which is 152, all over our population standard deviation, which is 28, over the square root of n, which is 56. Remember, in our calculator, we have a complex fraction. Thank you so much. See ya tomorrow, I guess. All right, so we have a complex fraction. So in our calculator, we really need to make sure to differentiate and say, okay, this is the top, so it goes into parentheses, and this is the bottom, so it goes in parentheses too to separate the two. So in our calculator, up top in parentheses, 145 minus 152 divided by the bottom, so in parentheses, 28 divided by the square root of 56. Oops. If you have a newer calculator like mine, notice that you have to use your arrows to scroll over to get out of your square root so you can put your other parentheses. So that way the calculator knows exactly how my fraction looks like. Thank you so much. See you tomorrow. Equals negative 1.8708, blah, blah, blah. Z values are always 2 decimals. It'll tell you that in the homework, but Z values are always 2 decimals. Negative 1.870, so our Z value would be negative 1.87. And that's it. And I don't usually like to put problems like that on 2 pages, but the reason why I did it is because I wanted to put all these graphs on 1 page. So let's use that and go to our next example. If you have a question, please stop me. But the next example says each of the following graphs depict a sampling distribution of X bar derived from the same population but using a different sample size. So everything's the same except a different sample size. So if the sample sizes were n equals 32, 53, 74, and 99, determine which sample size corresponds to which graph. So all these graphs are the same population with just different sample sizes. So we need to see, okay, how does the sample size affect the graph? So remember that our sampling standard deviation, sigma sub x bar, is going to be our sigma over the square root of n. This is the only thing that's changing. This is the only thing that's changing. Our mean stays the same. Our standard deviation is what changes. Let me go back and find that notes. We did that. Because the population mean is the same thing as our sampling distribution mean, so the mean isn't going to change, just that standard deviation. Going back, remember, the standard deviation is the spread. This is chapter 6 notes. Remember we did this? that changes the shape of our graph. So going here, if the mean stays the same, it's going to have to stay at the same center, stay at the same position, but we're going to have different spreads or different heights. Remember, if it's spread out or put together, so different spreads. So it's going to have different heights of our graph. So it's all centered around the mean. We just have different heights. All right, so we're going to have different heights, different spreads. So we need to see as the sample size increases, oops. As the sample size increases, as it gets bigger, notice the sample size as it increases, that means that denominator, the bottom of the fraction, thanks, Riley. See ya tomorrow. Have a good one. Bye, Taylor. See you tomorrow. Thank you for coming. So the denominator, or the bottom of the fraction, and the reason why I say that is, think about it. Whenever you have a fraction, when the bottom gets bigger, when you're dividing by a bigger number, what happens to the fraction? Think about it this way. If you have like 1 divided by 10, you have 0.1. If you have 1 divided by a million, you get 1e to the, so like 0.000001. So what's happening? It gets smaller. So it's going to get smaller. So the standard deviation, thank you, by the way. So the standard deviation decreases or gets smaller. So, moral of the story, if the standard deviation is going to decrease, if the standard deviation gets smaller, the standard deviation is our spread. So our spread gets smaller. And think about it, if our spread gets smaller, if we take our graph and we kind of squish it together, what about the height of our graph? It's going to increase, it's going to get taller. So it's going to look like tall and skinny versus wider and fatter, yeah. So it makes the graph look taller. So putting this all together, as our sample size increases, so looking from 32 to 53, 74, 99, as a sample size gets bigger, the graph is going to look taller. So looking at these graphs, this is our tallest graph down here at 0.4. So that means it's going to be our biggest sample size. So our biggest sample size is 99. So it's going to be n equals 99. And each time it's increasing. So this is our shortest one. So this shortest graph is going to be our smallest sample size. So n is 32. A little bit taller, the height goes to 0.3. So it's going to be a little bit bigger. So n equals 53. Then we go to 3 point something. So a little bit bigger. So n is 74. And then our tallest one, where our height is at 0.4, is going to be n equals 99. So as that graph gets taller, we get more sample size. Our sample size increases. So as the sample size gets bigger, the graph gets taller. A lot of times I like to write it out like in as simplest English as possible. So as the sample size gets bigger, the graph gets taller. All right, so let's actually take this and do something like we're doing in chapter 6. One more page and we'll take a break. Before I go there, questions on this one?
So you want to have to use the formula at all?
No, we just use the formula to derive like the reason why it happens. So because it's a fraction, the bottom's getting bigger, so the sample size is getting smaller. Sample size are spread's getting smaller, so it's getting more narrow. More narrow means taller. Thank you for asking. Yeah, Ryan.
These questions are only just looking for the height or width.
Right. Yeah, so look and be careful because sometimes it could be deceiving because of your scale. So look to see it like, so this is like goes to 0.4, it goes, let me go here. So 2 point something, almost 3, more than 3, and then 0.4. So we're looking at the height of our graph, which is a spread. Exactly. Thank you. Anything else? All right, let's go to page 4. Let me take a quick break and wrap it up. So our next example, straight from the homework, says the distribution of all registered nurses' salaries on the Treasure Coast is known to be normally distributed with a mean of $54,150 and a standard deviation of $850. Use the information to determine the two probabilities and round our solutions to 4 decimal places as needed. So the first thing says, find the probability that a single randomly selected nurse's salary is less than $54,436. And then the next problem says, find the probability that a random sample of 32 nurses have a mean salary less than $54,436. So I chose this problem because you can really see it's the same problem side by side. Because we're looking at just a single selected nurse, this is chapter 6. But then we're looking at a sample, which is chapter 7. So chapter 6, just like we did last class, versus what's new this time, chapter 7. So let's write down first what they give us, like always. So they tell us that it's normally distributed, so we can use the central limit theorem. Thank you so much. Have a good one. See you tomorrow. They tell us the mean, so our mu, is 54,150. And our standard deviation, our sigma, is 850. It asks us to find the probability that a single randomly selected nurse's salary, so we call that X, is less than 54,436. Let's draw a picture real quick. We know in the middle is our mean. Our mean, they told us in the problem, is 54,150. And we're trying to look for when that mean is less than, so everything's the left-hand side of 54,436. So it's somewhere to the right of the mean. Here's our X value of 54,436. And we're looking for less than, so everything on the left-hand side will be shaded. So just kind of like recapping what we did last class. Remember, this graph goes on forever. It's going on forever to the left towards negative infinity. In order to find the probability, we know the probability is going to be the shaded area. So to find the shaded area in our calculator, we did normal CDF. Normal because we have a normal curve. C because it's continuous. It's over this interval. Distribution. Then we did our lower limit. Our lower limit's going towards negative infinity. So negative 99999. Remember what's our lower. Our upper limit, our graph is stopping at the right-hand side at 54,436. Our mean that they give us in the problem is 54,150. And the standard deviation they give us in the problem is 850. So this is our mean and our standard deviation. So just straight what we did last week, chapter 6. In our calculator, remember it's second bars, which is our distributions, second bars, which is our distributions, going down to number 2, which is normal CDF. Our lower limit is negative infinity, so negative 99999 to represent negative infinity. Our upper limit is 54,436. Oops. Our mean is 54,150. Our standard deviation is 850. Remember, our mean is only 0 and 1 whenever it's normal. Whenever we're talking about z's, we're not talking about z's here, we're talking about x. Pressing paste should look exactly like we see it. On everyone's calculator, it should be the same. And we get 0, which is not right. Oh, thank you. 54,436. Thank you very much. There we go. Round of 4 decimal places and we get 0.63174. So our answer is 0.6317. That's just recapping and kind of seeing how it's different from last week to this week. So that's chapter 6. Same thing for chapter 7. It says find the probability, so it's still going to be the shaded area, but this time it's a random sample of 32. So that word sample is telling us our n value is 32 of nurses that have a mean salary of less than 54,436. So same graph, our mean is still in the middle, which is still 54,150. We're still looking at the same x value of 54,436. So it's going to be on the left-hand side of our mean. We're still looking at less than, so we're still looking at the left-hand side. Our graph is still going on forever to the left, so it's going on forever towards negative infinity. So we're still looking for the probability. This time we're talking about a sample, so this time it's going to be x bar is less than 54,436. Remember, our sample is x bar, sample mean. Before it was just a random single, so that's just x. This time we're talking about a random sample, so x bar. We're talking about their means. It's still going to be normal CDF. Our lower limit's still negative infinity, so negative 99999. Our upper limit's still on the right-hand side, 54,436. Our mean is still 54,150. Because remember, our mean is the same as our mean sub x bar. Here's the only thing that's different from chapter 7. Our standard deviation now is sigma over the square root of n. So we have our sigma, which is 850, divided by the square root of n, which is 32. So remember, this is sigma over the square root of n. That's the only thing that's different now. So in our calculator, the good thing whenever we go to second bars, normal CDF, everything should still be in there. So lower limit's negative 99999, upper limit's 54,436. Our mean is still 54,150, but now our standard deviation is 150 divided by the square root of n, so divided by the square root of 32. Pressing paste, pressing enter, there's our answer. So we get 0.97150, so it'll round to 0.9715. So looking at the same thing side by side, That's the only thing that's different.
I did not get that.
Why? Oh, you didn't get the answer? Or you didn't understand it, you mean?
No, what I did right.
So second bar is normal CDF, negative 99999, 54, 436, 54, 150. Okay, good. And then 850 over the square root of 32. Anything else? All right, the next one says the distribution of the ages of all IRSC students is known to be normally distributed with a mean of 20.1 years. So our population mean, because it says all, our mu is 20.1. The standard deviation is 6.3. It's talking about all, so it's talking about our population standard deviation. So sigma is 6.3. Use this information to determine the following probabilities, round to 4 decimal places as needed. So the probability that a random sample of 54, so it's telling us a sample, so it's going to be chapter 7, so n equals 54, has a mean age of less than, so everything on the left-hand side, 18.6 years. So let's do it. So probability of x bar being less than 18.6. Let's draw our quick little picture. In the middle is our mean, which they told us was 20.1. We're looking at our x value of, or x bar, I should say, of 18.6. So on the left-hand side. X bar, which is 18.6. And we're saying it's less than, so everything on the left-hand side. Going on forever towards negative infinity. All right, so normal graph, so still normal CDF. Our lower limit, looking at the left-hand side, is negative infinity, so negative 99999. Our upper limit, our graph is stopping at 18.6. Our mean is 20.1. Remember, we're talking about a sample this time, so we have to use our sampling standard deviation. So our standard deviation, which is 6.3, divided by the square root of n, so divided by the square root of 54. So that's the only thing that's new. It's our sampling standard deviation, which is sigma over the square root of n. So second bars, normal CDF. Our lower limit's negative 99999. Our upper limit is 18.6. Oops. Upper limit's 18.6. Our mean is 20.1. And our standard deviation is 6.3 divided by the square root of n, so divided by the square root of 54. Pressing paste, older calculator, newer calculator, it should all look the same, which is what we have written. Pressing enter, there's our answer. We get 0.04009 is going to round up to 0.0401. That's it. Same thing for the next one, but it says find the probability that a random sample of 54 students, so we still have that sample, so that's what makes it chapter 7. Remember, on the test, it's all going to be together. Yeah. So what's different here is you see that sample size, it tells you n, so whatever it tells you n, you have to do in sigma over the square root of n. So yes, lowercase n, the sample size. So see here how it said a single, that's what's chapter 6. Whenever it says a sample size, that word sample tells you it's chapter 7. Sample size is our lowercase n, so you have to do this extra step of sigma over the square root of n whenever it's sample. So the mean age, now it's going to be between 18.1 and 21.8. So we're looking for the probability that our sample, so x bar, is between 18.1 and 21.8. So the probability that 18.1 is less than x bar is less than 21.8. So everything's the same. So in the middle is still our mean, which is 20.1. Now it's in between 18.1, which is on the left, and 21.8, which is on the right. And we're looking for X bar in between the two. So it's still our shaded area, so it's still normal CDF. Our lower limit this time is 18.1. Our upper limit's 21.8. Our mean is still 20.1. And our standard deviation is still that sigma, which is 6.3, divided by the square root of n, so divided by the square root of 54. So same thing as chapter 6, the only thing that's different is now we have sigma over the square root of n. So second bars, normal CDF, lower limits 18.1, upper limits 21.8, our mean is 20.1, and our standard deviation is still that 6.3 over the square root of 54. Press case and look this for S calculator, which is what we have written down, and that's our answer, which is 0.96648. So it's going to round up to 0.9665. 0.9665. Let's keep rolling. Stop me if you have a question, please. But it says the mean weight of all Goliath grouper caught on the Treasure Coast is 379 pounds. Okay, it's talking about our mean of all. So that means our population mean, our mu, is 379. With the standard deviation, still talking about population, so it's still our sigma, of 61 pounds. Suppose a random sample, so our n value, lowercase n, is 70. So a random sample of 70 Goliath grouper from the Treasure Coast are caught and weighed. Determine the probability, so the shaded area, that the average weight of the sample of 70 Goliath grouper is within, I thought this weird wording was weird, within 17 pounds of the average of all Goliath grouper caught on the Treasure Coast, round to 4 decimal places. So remember, within means above and below. Or if you want to say add and subtract. So it's the same thing. I just put some weird ones on here. Remember, in the middle is still our mean, which is 379. And within 17 pounds, so 17 pounds below that, so 379 minus 17 would give us our lower boundary of 362. And 17 above, so 379 plus 17 would give us 396. So we're trying to find what is the sample mean, what's the probability that the sample mean is between 362 and 396. That word within means above and below. Now that we have it written, it's the same thing we've been doing. So our probability that our X bar is between 362 and 396. So probability that 362 is less than X bar. We're talking about a sample, so X bar is less than 396. So we still have our normal CDF. Our lower limit's 362. Our upper limit's 396. In the middle is our mean, which is 379. And then our standard deviation, which remember is sigma, which is 61, over the square root of n, which is 70. So because we have a sample, we have to go through and have this extra step of sigma over the square root of n. Second bars, normal CDF. Lower limit's 362, upper limit's 396. Our mean is 379. Standard deviation is 61 over the square root of n, so this over the square root of 70. Thank you so much. See you tomorrow. Pressing paste, pressing enter, boom, there's our answer. So our probability is 98028, so 0.9803. So the same exact thing as chapter 6, just because we're talking about a sample, we have to take that extra step and say our standard deviation divided by the square root of n. One more, we'll be halfway done, so we'll take a break. According to the National Weather Service, the mean daily temperature in Sebastian is 73.5 degrees Fahrenheit. So that's our mean. So let's go ahead and write that as our mu. Our mu is 73.5. With a standard deviation, so our sigma is 4.7. Consider the mean daily temperature in Sebastian for a sample of 71 randomly selected days. So our sample size, our n, is 71. Determine the probability that the mean daily temperature of a sample of 71 randomly selected days. Thank you. See you tomorrow. So probability, so it's still the same, normal CDF, find the area under the curve. That the mean daily temperature of a sample of 71 randomly selected days is less than the mean daily temperature by at least 1.4 degrees Fahrenheit. Round to 4 decimal places if you, again, weird wording, so that's why I wanted to put it on our notes. So in the middle is our mean, which is 73.5. And we're trying to find the probability that the mean of the sample is less than the mean daily temperature by at least 1.4. So less than 1.4. So whatever we're at our mean, 73.5 minus 1.4, which would give us 72.1. Or anything less than that, because it says is less than that by at least. So, or anything even smaller. So everything to the left-hand side, all the way towards negative infinity. Now that you see it, do you kind of see where I'm coming from? But I know, like, whenever I was doing this, I'm like, oh, this is kind of tricky, and I stop and think, so I figured you would have to stop and think. So that's why I wanted to do it together. So from our mean, 1.4 less than that, so 73.5 minus 1.4, that gave us our boundary of 72.1, and then everything less than that, so everything to the left-hand side. Now that we have our picture, it's the same thing we've been doing. So our probability, it's talking about a sample, so x bar being less than 72.1. For our note's sake, I just want to put a little note. We got 72.1, so it was 73.5 minus that 1.4. Our mean minus 1.4. Just for our note's sake, that's how we got that number. We're talking about normal CDF. Our lower limit's negative infinity, so negative 99999. Our upper limit, it's stopping at 72.1. Our mean they gave us in the problem was 73.5. And then our standard deviation is 4.7 divided by the square root of n, which is 71. Because we're talking about a sample, we have to do divided by the square root of n. Put this in a calculator, we're done. Second bars, normal CDF, negative 99999 for our lower limit, 72.1 for our upper limit. Our mean is 73.5. And our standard deviation is 4.7 divided by the square root of 71. So we press paste. It should all look the same, which is what's written on our paper. Press enter. There's our answer. There's our probability. 0.00603. So it'll round to 0.0060. While we're here, it said round to 4 decimal places, so that's why I want to put that last 0 to show that we did round it, and it was just 0. So don't stop it at 6 because it'll only look like 3 decimal places. So make sure to put 4 decimal places. So questions on this one before we take a quick break and then come back for the second half.
Anytime you see a sample, you're the point of the standard deviation divided by the square root of n.
Yes, exactly. Whenever you see sample, you know it's chapter 7. So whenever you see sample, you're going to take this extra step for our standard deviation and do standard deviation over the square root of n. Exactly. Only for sample. What? Okay.
Trying to explain it.
Oh, okay. Sorry. I didn't mean to call you out there. Can I help you or no? You got it. Okay. I feel like you don't got it, but that's fine. Let me know if you don't. All right, questions? All right, let's take a quick break and we'll come back and start off with chapters or page 5 through the end. the whole experience. All right, let's go ahead and let's wrap up the second half of this chapter. So we've been talking about sampling means and all that good stuff. Now we're going to talk about the central limit theorem for sample proportions. So same exact thing, but instead of a sample mean, we have proportions. Remember, proportions are just percents, which we know percents are just part of a whole. So whenever you see that word proportions, we're talking about percents, we're talking about parts of whole. So a proportion is the percent in decimal form of observations that possess a given characteristic. So for example, the percent of males, the percent in favor, something like that, the percents that we're looking for. Before we talked about X bar for our sample mean. Now we're talking about sample proportion. So that's where that P hat comes into play. So a sample proportion, which is similar to our sample mean that we've been talking about, which is X bar, is our P hat, which is the percent in decimal form of the sample that possesses the given characteristic. Remember, our population portion is going to be P, which our population portion is going to proportion is similar to our population mean. Oops. Which is our mu value. And it's the percent in decimal form of the population. So this is talking about population. This is talking about sample that possess a given characteristic. This is going to be our p-value. So you know how we have our mu, which is our population mean, and we have our sample mean, which is X bar. Same concept for proportions. Our population proportion is p. Our sample proportion is p hat. So whenever they have a hat or a bar up top, that's talking about our sample. So remember, proportions are part out of the whole. So our p-value, our population proportion, notice over here I put what all the letters are. So our p-value is our population proportion of capital X, which is a total number of elements in the population. So just like capital N means our population size, lowercase n is our sample size, uppercase X is talking about our number of elements in the population that possess a given characteristic, over capital N, which is a total in the population. So again, capital means population, lowercase means sample. P hat is our sample proportion. Lowercase x is the number of elements in the sample that possess the given characteristic. And lowercase n is the total number in the sample. So it's still part of the whole. So number of elements in the sample out of our sample size, divided by our sample size. Also notice we talked about this before, that our Q is 1 minus P. Q is 1 minus P. We'll talk about that in a second. So we talked about the central limit theorem previously, and we said that our sample size has to be greater than or equal to 30. But if we're talking about proportion, we're saying that the central limit theorem says that both n times p has to be greater than or equal to 5. And here comes our q. N times q has to be greater than or equal to 5. The sampling distribution of the sample proportion, because we're talking about sampling means, sample proportion now, is within a population mean mu and a standard deviation sigma. It'll be approximately normal, just like we talked about before. This time our mean, instead of sub p hat, or instead of sub x bar, we have sub p hat, is going to be our proportion, which is just our p-value, our population proportion. And our new formula for our sampling standard deviation, our sampling sigma sub p hat, our formula is going to be the square root of p times q all over n. Square root of p times q all over n. So unlike sampling distribution of X bar, the sample size of 30 doesn't matter. The 30 part isn't a thing anymore. We're talking about N times P has to be greater than or equal to 5, N times Q has to be greater than or equal to 5. Bear with me, let's do an example and then we'll come back. And it's all on here too, so just so you know. The population proportion, sample proportion, all these formulas are on here. Our mean was just our mu before, going back to what we did earlier. Now it's just our p-value, same thing. And instead of our sampling distribution of X bar formula, we just have a new formula. It's P times Q over N. Just a new formula, talking about percentages this time. Last but not least, we have our z-score formula, just like we did up here for X bar. We have our new z-score formula for our proportions. So it's p hat minus p, just like it was X bar minus mu, all over our standard deviation. This time our sampling standard deviation is going to be that square root of P times Q over N. I'm just moving it from here down here. All right, so same thing like we talked about, calculating the z-score. We have our p hat minus our mean of our proportion, which we know is the same thing as p, all over our sampling standard deviation, sigma sub p hat, which we said was the formula of square root of p times q over n. Just like we talked about before, nothing new. Just like we talked about before as well. Remember we said, can it be applied or can it not be applied? And we looked at n is greater than or equal to 30 if it's normal. So same thing here, determine if the central limit theorem can be applied to the sampling distribution of the sample proportion with each of the following sets of characteristics. Remember our what is that word? Our conditions are that n times p is greater than or equal to 5 and n times q is greater than or equal to 5. Before we looked at n is greater than or equal to 30 for our means. Same thing, we just have a little bit different formulas because we're talking about proportions. So our first one says if p is 0.1, just by stopping there, that means our q value is 1 minus p. So 1 minus 0.01. 1 minus 0.01, which would give us our q value of 0.99. And n is 19. So can we apply the central limit theorem? So our first thing says n times p has to be greater than or equal to 5. And n times q has to be greater than or equal to 5. That's what we're looking for. If yes, then it can be applied. If no, it cannot be applied. So n, which is 19, times p, which is 0.01, is that greater than or equal to 5? So 19 times 0.01, we get 0.19. Okay, well that's not greater than or equal to 5, so no. So the central limit theorem cannot be applied. I don't even have to check this one because it has to be both. I don't even have to check the other one because both have to work. 0.19 is not greater than or equal to 5, so it does not work. Same thing for the next one. If our p value is 0.99, that means our q value is 1 minus p. So 1 minus 0.99, 0.01. And n is 34 this time. Can the central limit theorem be applied? So same exact concept. We're going to see, okay, does n times p, is that greater than or equal to 5? And n times q has to be greater than or equal to 5. That's our conditions. So n, which is 34, times p, which is 0.99, is that greater than or equal to 5? So 34 times 0.99. So we get 33.66 is greater than or equal to 5. So yeah, that one works. Let's check the other one now. So n times q. So n, which is 34, times q, which is 0.01. Is that greater than or equal to 5? 34 times 0.01. And we get 0.34. So 0.34 is not greater than or equal to 5. So that means it can't work. They both have to work. So cannot. It cannot be applied. Same thing for the next one. If p value is 0.88, that means our q value is 1 minus p. So 1 minus 0.88. And we get 0.12. N value is 100. Can the central limit theorem be applied? So n times p has to be greater than or equal to 5, and n times q has to be greater than or equal to 5. So n, which is 100, times p, which is 0.88, is that greater than or equal to 5? We get 88. So 88 is greater than or equal to 5, so that one worked. Same thing with n times q, so n, which is 100, times q, which is 0.12, is that greater than or equal to 5? So 100 times 0.12, and we get 12. 12 is greater than or equal to 5. So because they are both greater than or equal to 5, then this means it can be applied. They have to both work. I put that here. Both have to work. Or both have to be satisfied, or whatever, however you want to call it. Last one. If p is 0.8, that means our q value is 1 minus p. So 1 minus 0.8. In my calculator, 1 minus 0.8 is 0.2. And our n value is 125. Can the central limit theorem be applied? So n times p has to be greater than or equal to 5, and n times q has to be greater than or equal to 5. So n, which is 125, times p, which is 0.8, is that greater than or equal to 5? So my calculator, 125 times 0.8 will give us 100. 100 is greater than or equal to 5, so that one's good, halfway there. Last one, n times q. So 125 times q, which is 0.2, is that greater than or equal to 5? And we get 125 times 0.2 is 25, is greater than or equal to 5. So that one works. So because they both work, yes, it can be applied. Question so far, baby steps. Question so far. Ryan.
This might be out of context for the question, but when you use the number 5, it compares us to
So because just like before we said 30 was just the rule, the theorem that they came up with. So theorem is just like a blanket rule in general. So for X bar, they said that the sample size had to be greater than or equal to 30. For this, the rule of thumb is 5. So n times p has to be greater than 5, n times q is greater than 5. Why 5? Honestly, I don't know, but that's the rule. So great question. What else? Anything else? So whenever we see p's and q's, we know we're talking about proportions. Same thing, whenever we see part of a whole, whenever we see a percent. All right, so let's keep rolling. So next page. So it says, if there are a total of 19,322 IRSC students, so in total, so that means that's going to be our population size. That's going to be capital N. 67% of which are under the age of 22. So because we're talking about the population and we're talking about a percent, That's going to be our population proportion, which is our p-value. Our population proportion, our p-value. Same thing, like it would be our population mean, but this time because it's a percent, that means it's a proportion. So in a random sample, so it's telling us our sample size. So n, which is our sample size, lowercase n. 68% are found to be under the age of 22. So because we're talking about the sample in this sentence, this is going to be our sample proportion. So it's going to be our p hat. Put it in parentheses. That's how I did the other ones, just to keep it consistent. Determine how many students in the population and the sample respectively are under the age of 22. Round your solution to the nearest whole number if needed. So it's just talking about percents. This has nothing to do with statistics. It's just talking about percents. So IRSU students are under the age of 22. So in general, this is going to be our population. It's just kind of wanting you to get used to proportions, get used to percents. So how many IRSU students in general are under the age of 22? So in general, our population, it says 67% are under the age of 22. So it's going to be 67% of our total. Our total population size, we said, was 19,322. So we need to find 67% of 19,322. Remember, to find a percent of a number, we're going to turn this into a decimal. Move our decimal 2 places to the left. So 0.67. Of means multiply. So times 19,322. So 0.67 times 19,322. And that will give us our answer, which is 12,945.74. Notice it says round to the nearest whole number if needed. So remember, just like the Panther problem, always round up. This one's going to round up anyways, but always round up. So 12,945.7 is going to round up to 12,946 IRSU students are under the age of 22. That's it. Same thing for the next one, but the next one says the students in the random sample of 940, so we're talking about the sample. How many students in the sample of 940 IRSU students are under the age of 22? So talking about our sample, we said that 68% of the sample, so 68% of those 940, same thing, move the decimal 2 places to the left, we get 0.68. Of means multiply 940. So 0.68 times 940 would give us 639.2. That's what I was just thinking. I think I just messed up because it doesn't say round up here. It just says round to the nearest whole number. So it just wants 639. It didn't say round up on this problem. It would say round up on the other one. Let me double check that on here because I assumed that it was going to round up. Give me 1 second. In my notes, I put 639, and that must have been what it said on the homework, but I just wanted to double check. I think so too. Okay. 0.66. Yep, that looks right. I just wanted to confirm on the homework so that way I told you the right thing. All right, other questions on this one before we get to the next one? So we're still kind of like slowly getting into the idea of proportions. So it says, according to a recent Pew Research poll, 64% of Americans say that the U.S. economic system unfairly favors the powerful. In a recent sample of 230 Americans, 144 agree that the U.S. economic system unfavorably favors the powerful. Determine the value of P and P hat, rounds to 2 decimal places as needed. Okay, remember P is our population proportion. That word proportion just means percentage. Where P hat is our sample proportion. And again, that word proportion just means our sample percentage. Round to 2 decimal places as needed. So it tells us put it in decimal form. If you also look back to on the previous page real quick, it says the percent in decimal form. So whenever we're talking about P hat and P, we always put it in decimal form. Ryan. That's okay.
Anything that has like above the letter, like P hat has something above the letter means the sample, and something
Exactly.
the letter by itself is a population.
Right. So the P hat and the X bar have like little things on top, have little hats on top. So that means sample, where just mu and P don't have anything up top. So that means population. You're exactly right. Not silly. All right. So the question says, in a recent poll, whatever, 64% of Americans say that U.S. economic system unfairly favors the powerful. So this is talking about our population. So that's going to be our P value. So 64%. Turning that percent into a decimal, moving our decimal 2 places to the left, would give us 0.64. Done. That's our p-value. For our sample, same thing, just not as straightforward. So in a recent sample of 230 Americans, 144 agreed. So that means 144 out of the 230 that are sampled. So 144 out of the 230 would give us, rounded 2 decimal places, 0.626, so 0.63. That's it. That's what we're talking about. Proportions, we're talking about percentages, we're talking about parts of the whole. Questions on this one? We're kind of like slowly getting our feet wet with proportion part. The next example says, suppose that 41% of voters in St. Lucie County support a proposed property tax. Consider the sampling distribution of the sample proportion of supporters with a sample size of n equaling 174. Determine the mean and the standard deviation of the sampling distribution of p hat. Round to 4 decimal places as needed. So it says, suppose that 41% of voters in St. Lucie County. So that means in general. So this is going to be our population proportion. This is going to be our p-value, 41%. Always turn that percent into a decimal. So moving our decimal 2 places to the left. So 0.41. And it told us that n is 174. By the way, because we have P, we also know Q. Because I know Q is 1 minus P, so 1 minus 0.41. Just writing out everything they give us. which is 0.59. All right, so it asks us, what is the mean of the distribution? So mu sub p hat, going back to our formula sheet, we said mu sub p hat is just our p-value. We already found our p-value. So our p-value we know is 0.41. And then what is the standard error of the distribution? The standard error, remember, is the same thing as our standard deviation. So, of the distribution, so sigma sub p hat. Going back to our formula sheet, we know that sigma sub p hat is the square root of p times q all over n. So the square root of p times q over n. So the square root, p which is 0.41, q which is 0.59, all over n which is 174. Square root of 0.41 times 0.59 divided by 174. And we get 0. It says to round to 4 decimal places, so 0.03728. So that'll round up to 0.0373. Remember, just not really that it matters, but we're able to use these formulas because of the central limit theorem. The central limit theorem says, don't worry about writing this, I'm just going to kind of write it just to be nerdy, I guess. So the central limit theorem says that n times p has to be greater than or equal to 5, and n times q has to be greater than or equal to 5. That's how we're able to use these formulas. That's how we're able to use these formulas. So n, which we know is 174, times p, which is 0.41, has to be greater than or equal to 5, which it is. So 71.34 is greater than or equal to 5, so that worked. And n times q, so 174 times q, which is 0.59, has to be greater than or equal to 5. 174 times 0.59, which is 102.66, it is greater than or equal to 5. So because they're both greater than or equal to 5, we're able to use these formulas. Are they going to give you a problem where they ask you for these formulas and it's not able to be used? No, they're not going to trick you. I just kind of wanted to explain maybe where the central limit theorem comes into play. We're able to do this because the central limit theorem lets us do this, and it's able to use the central limit theorem because it satisfies the conditions. Questions about that before we go to page 7? We have 2 more pages, page 7, page 8, and we're done. No, you're like, hurry up and get it over. All right, so next page. Putting this all together, like finally getting to the nitty-gritty here. According to a recent Gallup poll, it says that 71% of Americans report that they are better off financially today than they were a year ago. So this is our p-value in general. Doesn't talk about a sample yet, so it's talking about our p-value. Let p hat be the proportion of people in a random sample of 311. So this is our sample size, so this is n. Americans say that they're better off financially today than they were a year ago. Determine the following probabilities. Remember, probabilities is our shaded area. So we're gonna do the same thing, round to 4 decimal places as needed. So let me write down what they give us. They tell us our p-value is 71%. Moving our decimal 2 places to the left, which is 0.71. Just by knowing this, we know our q value because q is 1 minus p, so 1 minus 0.71 will give us 0.29. And we know our n value is 311. That's all we need. So find the probability, find the shaded area in a random sample of 311 Americans greater than, so it's going to the right, 72% say that they're better off financially today than they were a year ago. All right, so same thing we've been doing. Instead of our mean this time, we have our p-value. We have our population proportion, which is 0.71. So our probability that p hat is greater than 72%, which is 0.72. So notice instead of x bar, we have our p hat. So 0.72 is bigger, so it's on the right-hand side. And we're saying it's everything greater. We're shading everything to the right. Going on forever in the positive direction, so going towards positive infinity. Same thing we've been doing, nothing new here. So still normal CDF. Our lower limit is starting off at 0.72. Our upper limit is going on forever to infinity, positive infinity, so 99999. Our mean is the same as our p-value, which is 0.71. And then our standard deviation, remember our standard deviation is the square root of p times q over n. So the square root of p, which is 0.71, times q, which is 0.29, over this n, which is 311. So the square root of p times q over n. We're talking about a sample, so that's why we have to do this weird thing with the standard deviation formula. But it's the same thing like we've been doing. So normal CDF, so second bars, normal CDF. Our lower limit's 0.72. Our upper limit's infinity, so 99999. Our mean, which is our p-value, is 0.71. Our standard deviation is the square root, so second x squared of p, which is 0.71, times q, which is 0.29, divided by n, which is 311. Pressing paste, it should all look the same how we have it written. Pressing enter is our answer. Boom. Rounding to 4 decimal places, we get 0.34876. So it's going to round up to 0.3488. Stop me if you have another question, but we're going to do another one. Yeah, Ryan.
Can you minimize what's in the root before you put it in the normal CDF?
Yes, but be careful. So you're saying, can you actually like figure this out first?
Yes.
Yes, but just be careful about rounding. You have to go through like a lot of decimals so that way you don't round it and then put it in and then round it again. Yeah, exactly. So it's easier just to put it in there as a formula. Great question though. Can you do it? Yes, it's just gonna be more work. All right, let's do another one. So find the probability that in a random sample of 311 Americans, between 65% and 70% say they're better off financially than they were a year ago. So this time we're finding the probability, we're finding the shaded area, that p hat is between that 0.65 and 0.70. So in the middle is our p-value, which is 0.71. 0.65 is to the left. 0.70 is also to the left. And we're trying to find the area between the two. That it's between those two. So we're still going to do normal CDF. Reading our graph from left to right, our lower limit's 0.65. Our upper limit's 0.70. Then we have our p-value, which is 0.71. Then we have our standard deviation, which is the square root of p, which is 0.71, times q, which is 0.29, all over n, which is 311. Second bars, normal CDF, 0.65 times 0.70 times 0.71, and then I already have the standard deviation in my calculator, the square root of 0.71 times 0.29 all over 311. Pressing paste, it should all look the same how we have it written. Pressing enter will give us our answer. And we get 0.33891. So 0.3389 is our answer. That's it. Let's do another one. If you have a question, please stop me. If not, I'm just going to keep rolling for time's sake. So according to the New York State Board of Law Examiners, approximately 68 of people, that didn't help, taking the New York bar exam passed the exam. Are you kidding me? This is what it did yesterday. There we go. So this is talking about people in general. So this is going to be our p-value. So p-value is 68%, which is 0.68. So that means our q value is 1 minus p. So 1 minus 0.68, which is 0.32. Use this information to find the following probabilities, round to 4 decimal places if necessary. So if 10 people who have taken the New York bar exam are randomly selected, so this is our sample size, so n is 10. What is the probability that at least means greater than or equal to, which it tells us in the problem, 80%, so 0.80, have passed? Round your answer to 4 decimal places. Same thing. So we have our p-value in the middle, which is 0.68. We're looking for our p-hat value of 0.80, so it's somewhere to the right. And we're saying at least, so greater than or equal to, so everything to the right is shaded, going on forever towards positive infinity. So we have our normal CDF. Reading our graph from left to right, our lower limit is 0.80. Our upper limit's infinity, so we're going to plug that into our calculator as 99999. Our mean, which is our p-value, which is 0.68. And our standard deviation, which is the square root of p, which is 0.68, times q, which is 0.32, all over n, which is 10. Again, we're talking about a sample, so we have to do that weird standard deviation formula. Always when we're talking about a sample, you have to use the standard deviation sample formula. So second bars, normal CDF. Our lower limit's 0.80. Our upper limit is 9999999 for infinity. Mean, which is our p-value, is 0.68. And our standard deviation is the square root of 0.68 times 0.32 divided by 10. Pressing paste, it should all look the same how it's written. Pressing enter will tell us our answer. And we get our answer rounding to 4 decimal places of 0.20796 is going to round up, so 79 is going to round up to 80. So 0.2080. Let me put that as a note because people still get the rounding part messed up. So 0.207968, blah, blah, blah. We're rounding this 9. Looking next door is a 6. So 79 is going to round up to 80. 79 is going to round up to 80. Stop me if you have a question. If not, the next one says, if 42 people this time have taken the bar exam are randomly selected, what is the probability that at least 80, so same thing, have passed? But this time, the only thing that's different now, our n value is 42. That's the only thing that's changed. So in the middle is our p-value, which is 0.68. We're still talking about 0.80, which is on the right-hand side. And at least, so greater than or equal to, everything to the right, going on forever to the right, so going on forever in the positive direction towards positive infinity. We still have our normal CDF. Our lower limit's 0.80. Our upper limit's going on forever to infinity, so 99999. Our mean is still 0.68. Our standard deviation is still the square root of p, which is 0.68, times q, which is 0.32, all over n, which this time our n is 42. So everything stayed the same except that n value changed to 42. So if you have a newer calculator like mine, whenever you plug it in, it should stay the same. So second bars, normal CDF. Our lower limit is 0.80. Our upper limit's 99999. Our mean is our p-value, which is still 0.68. And our standard deviation is the square root of p, which is 0.68, times q, which is 0.32, divided by n, which is now 42. Pressing paste, it should look exactly like we see it on a calculator. Pressing enter will give us our answer. You look so enthused. Boom, there's our answer. So rounding, we get 0.04774, so it's going to say 0.0477. I wrote that kind of ugly. All right, then this last question for this page says, so why did the probabilities decrease? Why did the probabilities get smaller? Went from 0.2 to 0.0. So our option A says the probability decreased since the sample size increased. Remember, if you have a smaller sample size, that means a narrower distribution, a narrower graph, which if you have a narrower graph, it's going to reduce the area of the right tail. Or part B says the the probability decreased since the sample size decrease. I think I read that, whatever, you see it. Sample size increase or sample size decrease? Yeah, increase, thank you. I'm making it way harder than it is. It got bigger, that's it. Why did our probability get smaller? Because we went from a sample size of 10 to a sample size of 42. The population, dang it, the sample size increased. Let me just go to the next page. Questions on this one?
That's what I was saying as part of this chapter, because everything's like
Wordy.
similar, it's just a couple words changed.
Exactly. But I'm glad you said that, because I was thinking, I'm like, let me ask Taylor if she's still good, but then I forgot to ask you. So are you good now?
Yeah.
So far?
Like,
It's just wordy. Yeah, it's
Yeah.
wordy, and it's all, like you said, so similar, just very little changes. Which good and bad, I guess. Moral of the story, it's all the same normal CDF, but whenever you see a sample, do the different sample standard deviation formulas. Anything else before we go to our last page? All right, last page. So according to the Pew Research Center, 24% of Americans have not read a book in the past year. So that's our p-value. Doesn't talk about a sample yet, so that's our population proportion. Let p hat be the proportion of people that have not read a book in the past year in a random sample of 954. So that's our sample size, that's our n value. Americans, determine the following probabilities, round to 4 decimal places, and p hat values to 2 decimal places if needed. All right, so find the probability that a random sample of 954 Americans, at least 258 have not read a book in the past year. The reason why this one's weird is because it didn't give you a percent, it gave you a number. So first, let's start off with what they gave us. So our p-value, they told us, is 24%. Moving our decimal 2 places to the left, so 0.24. That means our Q value is 1 minus P, so 1 minus 0.24. Thank you. 0.76, and our N value is 954. That's all we need. So find the probability that in a random sample, so our P hat, at least, so less than or equal to, or I'm sorry, greater than or equal to, at least means greater than or equal to. 258 have not read a book, so 258 out of the 954. So 258 out of the 954. 258 divided by 954. So this will give us our P hat. So 0.27. It told us P hat values rounded 2 decimal places. So 0.27. So what's a probability that P hat is at least, so greater than or equal to 0.27? So this is our 258 divided by 954. So before it gave us the percent already, we just had to find the percent. But I knew it was a percent because there's percents in the problem, and it was part of the whole sample. So now it's just like every other problem. So our P value in the middle is 0.24. We're talking about our P hat being 0.27, so it's to the right side of our P. We're saying greater than or equal to, so we're going to shade the right-hand side, going on forever in the positive direction towards positive infinity. So we have normal CDF. Our lower limit's 0.27. Our upper limit's infinity, so 99999. Our mean, which is our p-value, is 0.24. And we're talking about a sample, so we have to use our sampling standard deviation formula, the square root of p, which is 0.24, times q, which is 0.76, divided by n, which is 954. In our calculator, then we're done. So second var's normal CDF, lower limit's 0.27, upper limit's 99999. Our mean is 0.24, and our standard deviation is the square root of 0.24 times 0.76 divided by 954. Pressing paste, it should look exactly like we see it on our paper. Pressing enter will give us our answer. Boom, done. Rounding to 4 decimal places for our probabilities, so 0.0150. Done. Same thing for the next one. It says find the probability that in a random sample of 954 Americans, between 200 and 267 people have not read a book this year. All right, so now our probability is between 200. So remember, it's 200 out of that 954. So 200 divided by 954 would give us our lower p hat, which is 0.209, so 0.21 is in between p hat being 267 out of that 954. And we get 0.279, so 0.28. So we're looking for the probability that our p hat's between 0.21 and 0.28. Same thing, they just gave us one extra little baby step of finding the percentages on our own. So in the middle is our p-value, which is 0.24. Our lower side is 0.21, so on the left-hand side of p. Our upper boundaries on the right-hand side, so 0.28. And we're trying to find the probability, the area between the two. So normal CDF. Our lower limit's 0.21. Our upper limit's 0.28. Our mean, which is our p-value, is 0.24. And the standard deviation is a sample, so it's going to be the square root of p, 0.24, times q, which is 0.76, all over n, which is 954. Second bars, normal CDF, 0.21s are lower, 0.28s are upper. Our p-value is our mean, which is 0.24, times the square root of 0.24 times 0.76 divided by 954. Pressing paste will put it exactly like we see it on our paper. Pressing enter will give us our answer. Done. 0.98307, which will round up to 0.9831. One last question and we're done. One last question and we're done. Questions on this one before we go to that last one? All right, according to recent research, 46% of Americans have less than $450 in the bank for emergencies. So that's going to be our p-value. So p is 46%, which is 0.46, which means that our q value is 1 minus p. So 1 minus 0.46. Which is 0.54. Let p hat be the proportion of people who have less than $450 in the bank for an emergency in a random sample of 78 Americans. So that's going to be our sample size. That's going to be our n value. So n is 78. Determine the probability that the proportion of people in a random sample of 78 Americans who have less than $450 in the bank for an emergency is within. Here comes this within word again. Remember, within means above and below. 6% of the population proportion. Round to 4 decimal places. All right, so just like we did before. In the middle is our p-value, which is 0.46. And we're going to go above and below. Above means adding, below means subtracting. 6%. So 6% is 0.06. Move our decimal 2 places to the left. So 0.06. So to go below 0.06, so 0.46 minus 0.06 would give us 0.4 for our lower boundary. And going above 0.46 plus 0.06 would give us 0.52. And we're trying to find the area between the probability that it will be between the two. So the probability that p hat's going to be between 0.4 and 0.52. For our note's sake, we got that 0.4 because it was 0.46 minus 0.06. And we got 0.52 because it was 0.46 plus 0.06. We went above and below 6% in decimal form because we're talking about decimals. So same thing, normal CDF. Our lower boundary is 0.4. Our upper boundary is 0.52. Our p-value is 0.46. And our standard deviation is the square root of p, which is 0.46, times q, which is 0.54, all over n, which is 78. Second bars, normal CDF. 0.4 is our lower, 0.52 is our upper, 0.46 is our mean, which in this case is our p-value. And our standard deviation is the square root of 0.46 times 0.54 divided by 78. Pressing paste will put it like we have it written. Pressing enter will give us our answer. And we get 0.98307. 0.71231. So 0.7123. Done. Last one. So determine the probability that the proportion of people in a random sample of 78 Americans who have less than $450 in the bank for an emergency is less than the population proportion by 19%. So less than by 19%, which is 0.19 or more. Round the solution to 4 decimal places. All right, so our p-value in the middle is still that 0.46. We're talking about less than 19%, so 0.46 minus 0.19 would give us that 0.27 or less. So everything to the right, going on forever to the right towards negative infinity. Again, just the weird wordiness. So we're looking for what is the probability that p hat is going to be less than 0.27. For our note's sake, we got 0.27 because it was our p-value, which is 0.46, minus that 19%, minus 0.19. So in our calculator, the normal CDF, trying to find the area under the curve to find our probability. Our lower limit is going on forever to the left towards negative infinity, so negative 99999 to represent negative infinity. Our upper limit's 0.27. Our p-value is 0.46. And our standard deviation is the square root of p, which is 0.46, times q, which is 0.54, all over n, which is 78. Second bars, normal CDF. Negative 99999 is our lower, 0.27 is our upper, our p is 0.46, and our standard deviation is that same square root of 0.46 times 0.54 all over 78. Pressing paste will put it how we have it written. Pressing enter will give us our answer. Ta-da! So notice we have 3.8019 blah, 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 e to the negative 4. Remember, e to the negative 4 is the same thing as saying 3.8019 blah, 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 times 10 to the negative 4th power, because it's scientific notation. So that just means you're going to move the decimal 4 places to the left. So 1, 2, 3, 4, filling in all of our gaps with zeros. So we would get 0.0003819, blah, blah, blah. The question told us to round to 4 decimal places. So 1, 2, 3, 4. We're going to round this 3. Looking next door is an 8. So that means our final answer is 0.0004. So make sure that you realize that E is our scientific notation. And that is chapter 7. So that's all of test 3. So hopefully it'll be a pretty good test for us. So questions, comments, concerns before I let you go? Let me stop recording.